All right, so we're going to talk about the definition of a limit here and how to use that um, to find the intervals uh, and show that something is a limit. So anyway, so here's the definition. So we let a function be defined on an open interval that contains a number a, except for possibly at a itself. We say that the limit of f of x as x approaches a is L, and we write this notation. If for every number epsilon greater than 0, there's a corresponding number delta 0 such that if the value of the function is within epsilon of the limit, whenever x is within delta of a. Okay, so maybe a picture will help a little bit better. So let's say we have, some graph, and we'll just use a straight line. Okay, so this is f of x. Now, it could be a curve or anything, okay? Now, somewhere over here, we have this value for x for a. And then over here, whatever its y coordinates, of course, is going to be f of a, right? So what this is saying is that if you pick any value for epsilon, go away, right? That here you get f of a minus epsilon, and this upper part would be f of a plus epsilon. That if you pick any value you want for epsilon, whether it be a billion or 0.0001, doesn't really matter, okay? That if this y coordinate is always between there, then there has to be some x delta, so that way whatever x that you have in here, all right, because there's like our little x is somewhere in that interval, okay? Remember the y coordinate somewhere in here, that this is going to be within delta, okay, that interval. So the distance between x and a is always less than some delta. And it's our job to find out what that delta is. What we want to know is how close can we squeeze that in? And if we squeeze this in really, really, really close, okay, then this is also going to squeeze in really, really close. That's what it's saying, okay? That you could pick some big interval out here, and you're going to have a big interval around the y coordinate. But as you move that in this direction, this is going to move closer and closer to the limit. And I should have put an L there, not an f of a. Okay. So it's to whatever the value for the limit is, because the function may not be defined at that point, but it's defined everywhere around it. And we can squeeze it as close as we want by squeezing x closer to a. So that's our goal. We have to find what those intervals are. So let's suppose our function f of x is just the linear function. Let's say that is 3x plus 2. Okay? And my claim is that I can get this thing to draw, that the limit as x approaches, let's say 4 of 3x plus 2 is going to be 14. All right. With that little notation stuff up there, we have two things going on. Okay, we have f of x minus L less than epsilon, and we also have x minus a less than delta. Okay. Now there's some relationship between epsilon and delta, and that's kind of what we're looking for. Now we're going to start with the f of x minus L. And we start with that because according to the definition, we get to pick any epsilon that we want. So that's kind of a given. Okay? Pick it to be a half, a fourth, a 5, whatever. Okay? And then we have to, from that, derive what this delta is going to be. It'll be in terms of epsilon. So we have the absolute value of 3x plus 2 minus 14. And we're going to say, okay, well, that's less than epsilon. We need to manipulate this until we can find in there the absolute value of x minus 4 less than something. And whatever that something winds up being is our delta. Okay? And that 4 is because there's the 4 there. It's always what the x is approaching. Okay? So now we just need to simplify a little bit. It's going to be 3x minus 12 is less than epsilon. Well, I don't know what I just wrote there. Less than epsilon. Now, how do we get an x minus 4 involved there? Well, I can factor a 3, and I can see, oh, if I factor a 3 out of that, that's going to be 3 times x minus 4. Now, the absolute value of 3 is just 3, so I could pull that outside of the absolute value symbol. Because, again, my goal is to find the absolute value of x minus 4. And I can do that by dividing both sides then by 3. Okay, so I know in this case my delta is always going to equal epsilon over 3. Because if I pick any epsilon, then I can use that little formula. So you know what, let's just say epsilon equals 1/2. Okay? Now, what that tells me, then, if epsilon is 1/2, okay, then the delta is going to be 1/2 divided by 3. So I'm going to just write it as multiplied by a third. So the delta is going to be 1/6. Okay, graphically, what that tells me is if I go back to this graph and say, your challenge is, okay, look, I want the y-coordinates to always be within 1/2. So this limit's 14, but up here is going to be 14.5, and this is going to be 13.5. If you tell me that, then I can turn back and say, you know what? We had a 4 for our a, right? Then x, all we have to do to ensure that the y-coordinate falls in that is that x is somewhere between 4 and 1/6 and 3 and 5/6. Okay? So as long as we stay within that interval, that's our delta, then we can guarantee our y-coordinate is going to be within the 14.5 to 13.5 range. Now, some of the homework questions give you a specific epsilon. Okay, so if you want that to be within 0.3 or whatever, you could just go ahead and replace the epsilon with whatever they give you. So maybe I say, okay, well, I know, let's say my claim here is that the epsilon as x approaches -2 of 2x minus 1 is going to be -5, and I want the maximum delta so that f of x minus L is less than 0.02. What I'll do is say, okay, well, we have f of x minus L has to be less than epsilon, right? So that means 2x minus 1 minus the -5 has to be less than 0.02. So let's see, 2x plus 4 then has to be less than 0.02. Now remember what I'm looking for, because the limit was x approaches -2, and I kind of want to keep my eye on the goal. I want that, or x plus 2 is less than whatever the delta needs to be. So keeping that in mind, I can see that if I factor out a 2, when I have this, I can pull the 2 outside of the absolute value. So x plus 2 then is going to have to be less than 0.02 divided by 2. And 0.02 divided by 2 is going to be 1. Wait a minute, that's not right. It's 0.01, all right. So then our delta in this case is the maximum value of it. The farthest we could get away is 0.01. So looking at the graph of this thing, so 2x minus 1 will look, something like this. Our x here at negative 2 says, whatever the limit is for this graph, okay, that if I want the y-coordinate, okay, to be within 0.02, then as long as my x-coordinate here is within 0.01, we can guarantee that that happens. But if the x-coordinate goes further out, okay, so if that x-coordinate were out here, it would no longer be in this interval that I want. So the furthest out I could get from negative 2 and stay with my y-coordinates where I want them is to have the x move either left or right 0.01. And that's the furthest I could go. I hope that helps with the definition of the limit stuff. And if not, let me know and we'll try again.